like to thank the organizers for the invitation. And this is a joint work in progress with Charles Bordenave and François Chapon. First of all, let me introduce some notations. For any n by n matrix, I will denote by lambda 1 of b, etc., lambda n of b, the eigenvalues of b, and by mu b, the empirical distribution of these eigenvalues. And I will denote by Sn of b, etc., S1 of b, the singular values of b. In 2016, with Charles Bordenave, we investigated this matrix model. Xn here is an n by n matrix whose entries are i.i.d. Standard complex random variables with finite fourth moment, and it's well known that then the norm almost surely converges to 2, the norm of the rescaled i.i.d. matrix. And we consider a deterministic bounded perturbation, an. We assume that for any complex number z, the empirical spectral distribution of an minus z star weakly converges towards some probability measure nu z on the half line. And under all these assumptions, actually, thanks to previous results from Dosier, Silverstein, and Tao et Wu, we can state that almost surely, when the dimension goes to infinity, then the empirical spectral measure of this deformed matrix model converges weakly towards some probability measure beta on the complex plane, which is completely characterized by these probability measures uz. And let us focus on two concrete examples of deformation. This matrix is a circulant matrix. It's a normal matrix with eigenvalues on the unit circle. And this matrix is a nilpotent matrix, and the difference between these two matrices has rank 1. Actually, it's easy to see that for any, whatever you choose the perturbation to be equal to this circulant matrix or this nilpotent one, the limiting spectral measure of an minus z star will be the push forward of the uniform distribution on the unit circle by this map. So that by the previous results of Dosier, Silverstein, Tao et Wu, we know that the limiting empirical spectral distribution beta of this matrix model will be the same whatever you choose the deformation an to be this matrix or this one. Moreover, it turns out that this limiting measure beta has a natural interpretation within the framework of free probability theory, thanks to Sniadis result. And it turns out that thanks to this interpretation, we can explicitly compute the support of this limiting measure, thanks to works of these authors. And it turns out that dealing with the circulant matrix or the nilpotent matrix as a perturbation, the limiting support, the support of the limiting empirical spectral measure of this deformed model is this annulus. And, excuse me. And, okay, the limiting support is the same. Nevertheless, we will see that these perturbations will show up different phenomena in the spectrum of this deformed i.i.d. model, as it is illustrated in the following slides. So here, this is a simulation of the eigenvalues in blue of this deformed i.i.d. model, where the deformation an here is a circulant matrix. You can see that all the eigenvalues are in the annulus, which is the limiting support, so that it seems that there is no outliers, I mean no eigenvalues that detach themselves from the rest of the spectrum and stay at some distance from the limiting support. Now, if we look at this deformed model, but when the, the deformation is the nilpotent matrix, this simulation exhibits outliers in the inner disk. So it seems that there are no outliers outside the maximum circle, but outliers in the inner disk. So to try to understand this phenomenon, with Charles Bordenave, we introduced the notion of well-conditioned perturbation. So let us fix some compact set gamma outside the limiting support, since we want to study the outliers, so eigenvalues that are outside the limiting support. And we say that a perturbation matrix AN is well conditioned in gamma if you can, if for any z in the compact set gamma, you can lower bound the smallest singular value of AN minus ZIN for all large n. And it turns out that actually this assumption on the perturbation ensures that it will not create outliers. Okay? If AN is well conditioned, then the deformed i.i.d. model won't have outliers in this compact set gamma. And let us come back to the previous examples. Remember that in that case, the limiting support was this annulus. And it turns out that indeed, it is easy to check that you can lower bound the singular values of the circulant matrix minus ZIN, so that indeed the circulant matrix is well conditioned in any compact set outside the limiting support. And therefore, this explains the fact, sorry, this explains, je ne sais plus. Là, je ne maîtrise plus du tout. OK. So this explains the fact that there is no outliers of this deformed model outside the limiting support. Now, what about the deformation by a nilpotent matrix? It turns out that it's easy to see that this nilpotent matrix is well conditioned out of the maximum circle. So that explains the fact that there is no outlier out of the maximum circle. But in the inner disk, the nilpotent matrix is badly conditioned, since the smaller singular value of nn minus z goes to 0 as n goes to infinity. So actually, with Charles Bordenave, we proved that when the xij's are Gaussian, I mean when the random matrix X is a Ginibre matrix, then the point process of eigenvalues of Mn in the inner disk converges weakly towards the point process of the zeros of the Gaussian analytic function with kernel is given by this formula. So Professor Mireille introduced the Gaussian analytic function this morning. This means that for any compactly supported continuous function, psi, the sum of psi evaluated in the eigenvalues of this deformed model converges weakly towards the sum over the zeros of this Gaussian analytic function G of psi evaluated at these zeros. And okay, now, so I go fast because we have a nice introduction this morning, so I don't need to reintroduce the notion Gaussian analytic function. Now, the nilpotent matrix N is a particular case of banded Toeplitz matrices. So, what is a banded Toeplitz matrix? Let us consider a Laurent polynomial A of lambda, on the unit circle. And a Toeplitz matrix, S and R are finite. And without loss of generality, we can assume that AS is different from 0. And a Toeplitz matrix is a L by N matrix whose diagonals are constant, and it is a banded Toeplitz matrix because all but finitely many eigenvalues are equal to 0. And the values of the diagonals coincide with the coefficients of the Laurent polynomial. And A is called the symbol of the matrix Tn of A. Now, we can ask, what about the spectrum of the deformation of an i.i.d. matrix by a general Toeplitz matrix when n is large? Actually, first of all, by the Afram-Parter theorem, it is known that the empirical spectral measure of Tn minus z, Tn minus z star, of the Toeplitz matrix minus z, Toeplitz matrix minus z star, converges weakly towards some probability measure nu z on the half line, so that, as previously, by Dosier, Silverstein's, Tao and Wu and Sniadi's result, we can deduce that the empirical spectral measure of these deformed i.i.d. models by a Toeplitz matrix converges weakly to almost surely towards some probability measure beta on the complex plane, and the support of beta is can be computed explicitly thanks to the works of these authors, and is equal actually to the curve A of S1, that is the image by the symbol of the Toeplitz matrix of the unit circle by the symbol of the Toeplitz matrix, and the union of all the regions where this integral will be greater than 1 over sigma square. So we know the convergence of the empirical spectral measure. We know the limiting support, but what about outliers? To describe the outliers, I need to introduce the so-called infinite dimensional Toeplitz operator. So it is an operator on L2, defined like this. And to describe its spectrum, according to the book of Butcher and Grutsky, I need to introduce the so-called notion of winding number. So we have our symbol of our Laurent polynomial on the unit circle. When W moves once around the counterclockwise oriented unit circle, A of W traces out a continuous and closed curve and the winding number of A is the number of times these curves surround the origin counterclockwise. And note that clockwise motion counts as negative, so that the winding number may be negative. And it turns out that the spectrum of the infinite dimensional Toeplitz operator is a union of the curve A of S1 and all the regions where the winding number of A about Z is non-zero. Let us consider an example. In this example, let us consider this symbol, which is just a polynomial. And when W moves on the unit circle, in red, you have the curve A of S1. So when a W moves on the unit circle, you start over there, you do like this. Oops, 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 okay? So that in all these regions, the winding number is equal to 1. In this one, is equal to 2. And in this one, is equal to 3, okay? And the support of the limiting empirical spectral measure of this 1000 by 1000 matrix, where Xn is chosen to be Gaussian here, and A is this polynomial. The limiting support has the frontiers of the limiting support is in black. Okay, can you see it? Yes. And the eigenvalues of this matrix are the blue points. And it seems that there are outliers. Excuse me, just to come back to the spectrum of the infinite dimensional operator. So the first conclusion was that the spectrum of the infinite dimensional operator is then all this region, okay, where the winding number is not equal to 0, okay, and the complement is this. So it seems, according to this simulation, that there is no outlier out of the spectrum of the infinite dimensional operator, but it seems that there are outliers inside. Okay? So, indeed, two very different phenomena occur, whether we consider outliers inside or outside the spectrum of the infinite dimensional Toeplitz operator. Let us start with the study of outliers outside the spectrum on the infinite dimensional operator. Okay. Actually, with François Chapon and Charles Bordenave, we proved that actually there is no outlier of a deformed i.i.d. model by a general Toeplitz matrix outside any epsilon fattening of the spectrum of the infinite Toeplitz operator. And I would like to notice that actually in 2020, Bazak and Zaitouni studied the outliers of a vanishing perturbation of a Toeplitz matrix. More precisely, they consider this matrix model, instead of rescaling by square root of n, they rescaled by n to the power gamma, with gamma strictly greater than 1/2, so that this matrix, the norm of this matrix vanishes when n goes to infinity. In that case, the support of the limiting empirical spectral distribution is different, since it's just the curve, A of S1. But the authors prove that there are, for large n, no outliers of this matrix model outside any epsilon fattening of the spectrum of T of A either. And there was also a work in the Gaussian case of Sochtern and Vogel concerning this model.
Excuse me?
Yeah.
Epsilon fattening?
Epsilon fattening means that you adjust the distance of the set. Okay, for an epsilon fattening of A. Okay. Let me present the main ideas to prove the fact that there is no outlier outside the spectrum of the infinite dimensional operator. We can rewrite our Toeplitz matrix as the sum of the circulant matrix plus some matrix Bn, which has a rank smaller than R plus S. And you can, this circulant matrix is obtained from the Toeplitz matrix just by adding these upper and lower triangular matrices. Okay? So that, of course, the matrix Bn is just the matrix where these upper and lower triangular matrices appear. Now it's easy to see that we can rewrite this matrix Bn as the product of two matrices, Pn and Qn, whose which one dimension is equal to R plus S. Okay, so it's easy to see that. And now remember that the limiting support is given by this explicit formula. And it turns out that the circulant matrix is a diagonalizable matrix, and with eigenvalues on A of S1, so that it's easy to see that it is well conditioned in the sense of Charles Bordenave and myself in any compact set outside the complement of the support, since A of S1 is included in the support of beta. And therefore, by our result with Charles, we can deduce that almost surely for all large n, this deformed model, this perturbation by this circulant matrix, the general circulant matrix, has no outlier. Now, okay, so we wrote the Toeplitz matrix as a sum of the circulant matrix which do not create outliers, plus the product of two matrices having one dimension equal to R plus S. So to shorter notations, let us set Y to be the rescaled i.i.d. matrix and R Y plus C to be the resolvent at any point Z in gamma, gamma being a compact set in the complement of the support of beta. R Y plus C is the resolvent at any point Z of Y plus C, Y plus the circulant matrix. We know that it is well defined since this matrix has no eigenvalue in gamma. Now, so the determinant of Z minus Mn. Mn is our deformed matrix, is equal to the determinant of Z minus Y minus the Toeplitz matrix, so that now we can factorize this determinant by using the resolvent of Y plus C. And thanks to the Sylvester's determinant identity, we can rewrite this determinant of a n by n matrix as the determinant of a R plus S by R plus S matrix. And therefore, we have obtained that the eigenvalues of our deformed model in gamma are exactly the zeros of the determinant of this R plus S by R plus S matrix. And now the idea is to find the asymptotic of this function. And the idea to study outliers of random matrices thanks to Sylvester's formula was initiated by Laurent Georges and Raj Rao. So actually we can do exactly the same, dealing now with just the deterministic matrices. And we can do exactly the same now, factorizing by the resolvent of the circulant matrix, since the eigenvalues of Cn of A are all in A of S1. This is well defined. And similarly, using Sylvester's identity, we can obtain that we can factorize the determinant of Z minus our Toeplitz matrix that way, so that finally we obtain, thanks to this Sylvester's identity, that the eigenvalues of our deformed model are the zeros of this analytic function Fn, and the eigenvalues of the Toeplitz matrix are the zeros of the analytic deterministic matrix, which is equal to this ratio of determinants. Okay, but actually it can be proved using iterating resolvent identities. It can be proved that this random matrix, this R plus S by R plus S random matrix, is very close to this deterministic one, so that using Hadamard's inequality for determinant, we can prove that almost surely this function Fn, whose zeros correspond to the zeros of our matrix model, is very close, uniformly in Z in gamma, to this deterministic function. So the idea is now, can we use Rouché's theorem? For this, we have to handle, at least on the frontier of gamma, we have to have some lower bound of this ratio. And this will be okay thanks to Seger's strong limit theorem. Indeed, note that actually Z minus the Toeplitz matrix with symbol A is actually equal to a Toeplitz matrix with another symbol B, which is just Z minus A. And it turns out that since we deal with Z outside the spectrum of the infinite dimensional operator T, the winding number of this B is equal to 0, since we are outside this spectrum. Okay? And these are exactly the conditions to apply the so-called Seger's strong limit theorem that describes the limiting behavior of the determinant of the Toeplitz matrix Tn of B. And this Seger's strong limit theorem actually allows us to obtain this lower bound for this ratio of determinant. Therefore, we can apply Rouchet theorem and conclude that the analytic functions fn and gn have the same number of zeros in gamma. But because actually this lower bound is valid for any z in gamma, we see that gn has no zeros in gamma, so that we can conclude that fn has no zeros in gamma, and therefore there are no eigenvalues of mn in gamma for n large enough. And by the way, we can see also that the Toeplitz matrix has no eigenvalue in gamma. So this completes the proof of the fact that there is no outlier outside any epsilon fattening of the spectrum of the infinite operator. And now what about outliers in the spectrum of the infinite dimensional operator? And so what is still true? It's still true that the eigenvalues of Mn are the zeros of this analytic function. And it's still true that Fn are very close to, uniformly close to this deterministic and analytic function. But now this ratio goes to 0 as n goes to infinity, when for any z in the spectrum of the infinite Toeplitz operator minus this curve. So Rouchet's theorem no longer applies. So to describe the outliers now in the spectrum of the infinite Toeplitz operator, I need to introduce some terminology. So for any connected open set D, we can consider h of D, the space of complex analytic function in D, and we can endow it with this distance, which makes h of D a complete separable metric space, and we can equip it with Borel sigma field, and the random analytic function on D will be just an i.i.d valued random variable. And now, for a non-zero analytic function, we denote by ZF the set of its zeros, and we define the zero process as the sum of the Dirac mass at these zeros, counting multiplicities. And here is a fundamental result by Professor Mireille that we will use in the following. Assume that you have a sequence of random analytic functions, xn, which converges in law to some analytic function x. Then the zero process of xn converges in law to the zero process of x, provided that almost surely x is not the null, the vanishing function. And so this will be fundamental for us. Let us come back to our problem. Remember that we consider we try to find the eigenvalues of Mn which are outside the spectrum of the infinite dimensional operator T of A. So let us fix a compact outside the limiting support of our deformed model, but inside the spectrum of the infinite operator, infinite Toeplitz operator. We know that the eigenvalues of our deformed model in this set gamma coincide with the zeros of this analytic function Fn, and we know that unfortunately, Fn goes to 0 as n goes to infinity. So the idea now is, are we able to find some other scaling parameter theta n and some non-zero random analytic function f such that theta n Fn weakly converges towards this f? If the answer is yes, then from Professor Shirai's result, we could deduce the convergence in law of the zero process of theta n Fn, but the zero of this function is still the eigenvalues of Mn, towards the zero process of f. So keep this in mind. So remember that the eigenvalues of Mn are the zeros of this function Fn, which is by definition the determinant of this R plus S by R plus S matrix. So we saw that this random matrix is close to this one, which is deterministic. So that let us rewrite this matrix as a sum of this deterministic matrix Hn, which is the identity plus this one, plus this error term, which is random. And we know that, this error term goes as n goes to infinity, goes to 0. It turns out that actually this deterministic matrix converges quite fast to some deterministic matrix H. I will give a flavor of this matrix at the end. Now, what about this random part? To describe the behavior of this random part, I need to just introduce the notation. I will, between two process un and vn, I will use the notation to say that the Lévy-Prokhorov distance between the finite dimensional distribution of un and vn goes to 0 as n goes to infinity. And actually, we are able to prove a central limit theorem for the random, the error term, sigma n, thanks to a multivariate central limit theorem for traces of product of deterministic matrices and an i.i.d matrix. Thanks to such a multivariate central limit theorem and the rewriting of sigma n as the infinite sum of things like that, we can establish that actually when we multiply sigma n by square root of n, the finite dimension, the Lévy-Prokhorov distance between the finite dimensional distribution of square root of n sigma n and the finite dimensional distribution of this analytic process goes to 0. This analytic process is a sum of two analytic processes. The first one, I assume this by just too easy exposition. The n is the sum of these two processes. The first one is the Gaussian analytic matrix, which is independent from xn. And this process involves xn here, which is our i.i.d matrix, and these matrices which are deterministic. So, now let us come back to Fn. Fn is the determinant of Hn, the deterministic matrix, which converges towards H, plus some random term. We can make a further expansion of the determinant so that we can rewrite Fn as a determinant of the deterministic matrix plus the sum on the higher derivatives of the determinant map at the point Hn of z applied to sigma n. Now, a miraculous phenomenon occurs. We don't really understand why, but it's quite miraculous for us. Is that actually, if you you consider a point z in the region where the winding number is equal to some delta, some fixed delta, this delta is exactly the first order of the derivatives of the determinant map at h of z, which is not identically 0. This is exactly the first order where you are not identically 0. So the idea, okay, is to rewrite this determinant as the sum of the derivatives of the determinant which are at order lower than delta. The determinant, the derivatives, sorry, of order delta and the higher order derivatives. Well, we know that each term of this equality goes to 0 as n goes to infinity. But now, let us multiply everything by square root of n to the power delta. Of course, the zeros of Fn, or that is the eigenvalues of Mn, are once more the zeros of this function. But now, we know that because Hn goes quite fast to the deterministic matrix H, and because of this, all these terms, all the first terms will go to 0 when n goes to infinity. Now, what about the last terms? Actually, we have sigma. Here we have delta square root of n, but we have some sigma n left. But sigma n goes to 0. So that this explains the fact that these, all these terms go to 0 when n goes to infinity. So that we are left with only this term, which is the delta derivatives of the determinant map at a point h of z, which is evaluated at the analytic process Zn involved in the central limit theorem. Okay? And therefore, we obtain the fact that the zeros we have, so this gives us the convergence of the towards 0 of the Lévy-Prokhorov distance between the finite dimensional distribution of square root of n to the power delta Fn and this analytic process. And then using proving tightness of these processes, thanks to Professor Shirai's criterion for random analytic functions, and using the previous theorem on zero process, we obtain the following. We obtain the following result with Charles Bordenave and François Chapon. We obtain that if you consider a compact set which is in the region where the winding number of the symbol is equal to delta, then the Lévy-Prokhorov distance between the point process of eigenvalues of our deformed model and the point process of zeros of this random analytic function goes to 0 as n goes to infinity. And just to give you a flavor of the objects, I will present you the formula for fh of z and the formula for the covariance of this Gaussian process. So here the covariance of the Gaussian process, and which involves, of course, the symbol A. And here is, in full generality, the formula for the deterministic matrix H. Oh, I think I haven't. I forgot to say that, unfortunately, this result at this moment, we are just able to prove it when R is equal to 0, and but it's a work in progress to understand the general case. And okay, yes, I would like to conclude with some remarks. Is that actually the limit process of outliers turn out to be non-universal. Indeed, the process Zn depends on the distribution of the entries of the i.i.d. matrix through this term. Moreover, it depends through this delta on the regions of the complex plane. And what was the other remark? Sorry. And moreover, even when the i.i.d. matrix is a Gaussian one, there is no regions where there is no reason, sorry, that the limiting process is Gaussian when the winding number is different from 1, since this is not linear. When delta is different from 1, this is not linear in the xn, so that there is no reason for the process to be Gaussian, even in the Gaussian case. In the xn is a Ginibre matrix. And similar phenomena were previously brought out by Bazak and Zaitouni when they studied the outliers of vanishing perturbation of Toeplitz matrix, and also Sostrand-Vogel studied outliers for B-diagonal Toeplitz matrices. So they brought out very similar phenomena. But actually, even at this moment for R equal 0, our method using Sylvester's determinant identity can be used to recover the work of Bazak and Zaitouni. And in that case, yes, when the perturbation, since they consider vanishing perturbations of Toeplitz matrices, in the case of Bazak-Zaitouni, it will be only this term left. This term will be not present. So the method is different, but we can recover the results by our method too, at least for R equals 0 at this moment. So thank you very much for your attention.
Are there any questions or comments for Mireille?
Question? That's a technical question. It's about this miracle.
Yes.
Le miracle.
Oui.
Yes. So the derivative for less than k, delta is 0. At k, it's not 0.
Yeah.
So what is this derivative? Is it a complex derivative?
And it's just the usual derivatives of the determinant map. And actually, you can, the problem is to, actually the problem is to know the rank of this matrix H, and sorry for my English. On attrape, we catch this rank thanks to this property on determinant. And I don't know if it's clear or.
It's curious for me because the derivative before the less are 0, and at some points they are not 0. In fact, I used to see something can be once we have derivative 0 after some rank, but not before. When we derive.
No, but it's they are identically 0. For any case, they are identically 0 before delta.
Before delta.
Yeah, meaning that the rank has to be lower than. Yeah.
Okay. But at this,
yeah.
Thank you.
I have just a repetition question. Can you remember? I don't remember where the non-universality comes from.
Okay. Okay, the process, Zn, is the sum of these two guys, and Xn is, by definition, the matrix, the n by n matrix, whose entries are independent random variables with some common distribution mu. And when I said there is no universality, is that the process Zn depends on the distribution of the matrix Xn, of the distribution of the entries of matrix Xn. In the sense, it's not universal. If there is not this term, it will be universal since this is Gaussian. But we have this term, so it's not universal.
Is it more clear?
Actually, I have a related question. So, could you move beyond the Gaussian with? So here everything is Gaussian, right?
No.
Oh no, it's not.
Xn, you mean?
Yeah.
No, Xn is it's not. We have technical conditions on the xij's, and this is just to make the presentation easier. But no, X is general.
So if there are no more questions, let's thank Mireille again.